Swayam Prabha. Digital India. Educated India.
Welcome back. Let's talk a little bit more about alcohols, the stuff that we all like sometimes. So let's look at some of the reactions. We talked about halogenating them to make them more reactive because we know alcohols have a very non-reactive functional group. It's not going to leave. It's pretty happy. It's almost like water. So it's neutral. We saw how to functionalize that. We made them into halogens. We can also oxidize them. We can reduce things to make them into alcohols, and that's what we're going to look at today. Let's look at some redox reactions, reduction and oxidation. So we talked, a little bit about oxidation numbers from before, hopefully a lot. And let's say we can take a series like this. Let's say you can take carbon. This is the most reduced form, like your gasolines are all in a very reduced form. They've been underground for millions of years, no oxygen, and they're all in a very reduced form. And hydrogen's always +1, so here's +1 for hydrogen, and there's times 4, and let's say we put an x for that. 4 times +1 plus x is going to be, it's a neutral molecule, 0, therefore x here is going to be -4. That's the most reduced form. You can't reduce carbon more than that, okay? It's a quadrivalent molecule. So here's a carbon at -4 oxidation number. Let's say what happens if you put an oxygen on that. So oxygen, we know, or most of the time it's -2. So if you do that and put an x for carbon, so 4 -2, so there you're going to have an oxidation number here, 4 plus 4 -2, so therefore carbon has to be -2 to balance it off. Let's see what happens if you put 2 oxygen bonds. So you can take carbon, and this is now, you can see -4 to -2. It got oxidized. Now here, this is +1, +1, -2. Therefore, carbon here, 0, -2, +1, +1. Therefore, x is 0 for the molecule to be 0. Now, you can add more oxygen to this. And here we go. Let's say I add another oxygen here. So you're going to be -2, -2, +2. So the carbon has to be +2 in order to balance that out. So you're getting more and more oxidized. And then you can add another hydroxyl, or maximum you can do this. So that is going to be carbon. Now this is going to be -6 +2, so carbon has to be +4 to neutralize that. So you can see that is going to be the maximum. So we can go all the way from -4 to +4. That's the range for carbon. Now you can take off a carbon dioxide, and this can go to carbon dioxide, like in a Coke. When you open up a Coke can, there's carbonic acid that becomes carbon dioxide and water, and you can see carbon dioxide, this is -4, so carbon has to be +4. So carbonic acid and carbon dioxide pretty much have the same oxidation number. So we are going to do some reactions where we are going to take this and go over and oxidize them to these molecules. And we can also do the reverse. We can pump hydrogens into this and go from here to here as well. So that would be reduction, and that would be oxidation in the opposite direction. Let's start with reductions. We can do reductions on carbonyls with carbon double bonded oxygens to get them to go to alcohols. So let's say I take something like this, and the most common way to do this in industry is with some metal. So hydrogen gas with, let's say, platinum or palladium or some metal here that's going to absorb or palladium or nickel, and like hydrogenation in margarines, okay, they take oils and solidify them so you can spread them, even though the solid form is actually worse for you than the liquid form. So here your hydrogen can go on there and it can reduce it, and you can put a hydrogen on either end of that pi bond, and just like we did with alkenes, no difference. The thing about this is going to be very high temperature and pressure, so it's really not viable in a lab. So here, if let's say you have an alkene, you're going to add hydrogens there as well. So this is a method that's good if you want everything in your molecule hydrogenated. Let's see what we can do if we don't want alkenes to be reduced and only want the carbonyls to be reduced. This is pretty much the most common way of doing this. Let's say I have an alkene like that, and I can add to this a molecule that's a hydride reducing agent, not hydrogen, but hydride. So I can add to that something that will have a H minus, and an H minus can be made by taking boron, which is group 3, so it's electron deficient, and pumping hydrides into it and making it very, very hydride rich. It's actually a nucleophile now. Boron now has got 8 electrons. So this hydrogen can come in and deliver here to this carbon hydrogen and make a CH bond. And oxygens, you know, have got lone pairs and they're nucleophilic, and that will then go to the electrophilic boron. And sometimes you may have seen a 4-member transition state for that they have drawn, where you are breaking the pi bond, giving it to the boron, and the hydrogen adding and breaking away from the boron. And so this is something you may have seen. The sodium borohydride is like the most common reagent for this, and you can do this in methanol. Methanol is something that is protic, but it's neutral. It's not an acid or a base, so it's really not going to eat up any reagents. The methanol is then going to be used for workup. So here you can take this, and then it's going to fall off into a boron on the oxygen and a hydrogen here. So BH3 here, and then this is going to then go on and reduce other things. So let's say this is an OR group. We can put OR, 4 of them on here. And I'm not going to draw all 4. I'm just going to put OR 3 minus. I'm going to draw this out. And the nice thing is, if you have a pi bond, the pi bond is not affected by hydride, because hydride is a nucleophile, pi bond's a nucleophile. They're not really interested in each other. And so here's your counter ion, and you put all of those hydrides onto the carbon now, and we got 4 of them. So it just does this 3 more times. And now we can take the methanol right here and hydrolyze it. Okay, I'm going to put the methanol in a different color. So you're going to, let's say if you have methanol here, and this may happen stepwise, you want the oxygen now to become free and become an alcohol. So you're going to want to break the oxygen boron bond, and well, this may happen stepwise, but I'm just going to do this. This is going to be 1, and this is going to be 2, and this will happen with each one of this. So your BOR3 will become BOCH3 now. I'll just do 1 for right now. So you will have your methanol broken up, and you will have oxygen with a hydrogen from the methanol. And that we know, even if you put a deuterium, it's going to end up there. Then we have the boron now with OCH3. Boron goes with your OCH3. And that's going to happen 4 times, because each one of this is like this. This will happen 4 times. So you will have BOCH3 3 times and NaOCH3 with the sodium. This plus this. So this is going to happen 3 more times. And I'm just going to put this here. Each OR alkoxide will be replaced by methoxide. Do it 4 times. And that's how you would reduce it. And as you can see, this is chiral. And here this is flat, so you can add above and below. So you will not just get this molecule, let's say you will get about 50% of this, because this is chiral. If you take chiral, then you can't even tell, plus you will get 50% of the mirror image. So you will get about 50% of the one where you have oxygen at the bottom and hydrogen at the top. So hydride can add from above or below. So you'll get enantiomers in this case. Again, there is no real rule for this. For example, if I brought it with a methyl group sticking up for each one of these, then you'll have a methyl group sticking up here, they'll become diastereomers. So this particular case, they're enantiomers. So that's borohydration. Now, if you have aldehydes and aldehydes already have a hydrogen, you put another hydrogen and it will become primary alcohol. And in this case, you have a ketone and the ketone becomes a secondary alcohol. I'll put a note, does not, so you cannot go from here to here. It only go from here to here. Does not reduce esters or acids. If you want to use esters and acids as starting materials, and esters are really very common in plants, their fats are pretty much esters. You can take esters and then make them into alcohols as well. But not with sodium borohydride, but with a close cousin. So boron is group 3, and so right below boron is aluminum. Now when you go down the group, you know the reactivity of metals increases, right? So aluminum is a lot more reactive than boron. So we've seen BH3, this is a little more reactive than BH3. We can look at lithium aluminum hydride. So LiAlH4, lithium aluminum hydride. All right, so here let's take an ester. These are more commonly used for the esters and the acid. We can use lithium aluminum hydride here, but it's kind of an overkill because, you know, sodium borohydride, you can do it at room temperature and it's not going to explode. Whereas the lithium aluminum hydride, the minute you use that, you have to be, you know, sometimes in a glove box, and it's very, very reactive. So it's much ado, okay? So let's look at some esters that we can use. This is an ester, let's say OCH3, it can be any ester, any R group, and we can use this and use lithium aluminum hydride to reduce it. And lithium aluminum hydride and borohydride, as I said, are close cousins, and so here aluminum, AlH3 is the most common, but you can put in lithium hydride into that and it will become a negative aluminum and a counterion lithium. Now this aluminum, AlH3, is electron deficient, so when you take the hydride off, the pi bond will then go with the AlH3, which is going to be electrophilic. So this is your nucleophile that's going to attack that. And so now you will have a carbon, and then the oxygen goes with the Al. So now you have a hydrogen here, and you have AlH3 here. And so when you have 4 things on aluminum, aluminum is group 3, 3 minus 4 is a -1 formal charge, and the counterion is lithium. Now we have an oxygen and an R group. I'm just putting methyl, it can be any R group. And anytime you have a carbon with 2 oxygens or 3 oxygens, these oxygens are electron heavy. They are loaded with electrons, so they just don't like too much of that repulsion inside the same molecule, in fact around the same atom. So they're kind of fighting it out for space. And this one, well, this bond here is not very strong, oxygen aluminum, not stronger than, let's say, this. So this is going to come down and push that out. And that can go with the aluminum. So here we will have now a carbonyl, CO, and the OCH3 left, and you have an aldehyde. And those are very desirable compounds, except in this case, you still have your aluminum now with more hydride. So those hydrides want to kind of get off and form stronger bonds. Aluminum hydride bonds are kind of weak, but carbon hydrogen bonds are very strong. So they want to do it all over again. So here's your hydride, steps out. It's easy to break this bond. Now it forms a very strong alliance there. And the oxygen will then go over here. And you're going to get your carbon oxygen, same deal. And you will have your aluminum, H, and you will have two hydrogens, CH bonds. CH bonds are really very, very strong. So now this is going to happen, and then you have your OCH3 on there. Now, once you've done lithium aluminum hydride addition, you're going to add twice because the aldehyde is quite reactive and it's going to seek out another hydride. So you are not going to stop here. You will keep going. So now you're going to take this and, well, once your reaction's all done, you want to have a neutral oxygen. So you just throw in some HCl, aqueous HCl, which is basically H3O plus. And that is going to then protonate that and give you a neutral alcohol. This can be ammonium chloride, which is slightly acidic, and that's usually what we use for workup is ammonium chloride. This is called the workup step. You don't want to put this with this, okay? There's going to be a huge explosion and you might see the sky right there in the middle of your lab. So you don't want to do that. So you want to do this after this is reacted, then you put this in and then you just take off that aluminum and put your proton on there. So you get a very nice primary alcohol. And this came from the water and these came from the lithium aluminum hydride. So if you start with an ester or even a carboxylic acid for that matter, for carboxylic acid you have to take off the hydrogen first and then this reaction will happen, and this is going to be primary. Plus your aluminum is going to just go off and it'll become AlOCH3 and get hydrolyzed, and you end up eventually with aluminum hydroxide. But for right now, I'm just going to put AlH2OCH3 and water. And this is going to get hydrolyzed further. So that's one of the good things about lithium aluminum hydride. And another nice thing is, let's say you had an alkene way out here. It's not going to touch that alkene, as we said. H minus is a nucleophile, alkene's a nucleophile, and your alkene's going to remain throughout the entire journey. And eventually all of these are going to get replaced. The hydride's going to go and you will get aluminum with 3 OR groups. Now that's reduction. If you have aldehydes, primary, ketones, secondary, esters, and acids, carboxylic acid, RCOOH, these will both go to primary. You cannot make secondary alcohol with this. We cannot really ever make tertiary because tertiary alcohol will have 3 R groups, no hydrogen. So you cannot use hydride reduction or hydrogenation to make tertiary. You can only use them to make primary and secondary. Here too, if you use a ketone, you will get secondary. And if you used an aldehyde, you would get primary. Tertiary alcohols, which are like this, there's no H here, cannot be made by reduction. So these redox reactions are for mainly primary and secondary, because if you put a hydrogen on here, one of these should be hydrogen, but on a tertiary there's no hydrogen. There are 3 R groups, so you can't really make them. Let's look at oxidation. Now there are a lot more oxidation reactions and we'll look at some, and I think I may not have space to write all of them. Those are the most common reduction methods. Let's do an oxidation reaction. So oxidation, let's say, is going to be when you have hydrogens being removed. So here we added hydrogens, and if you remove hydrogens, then that's called oxidation. So you take these off, minus H2, whatever way you're going to take that off, you are going to put a double bond. That's oxidation. So you're basically going in the reverse direction. So you're going from like -2 to 0. All right, let's look at a simple one. Let's look at the most common way of doing this, and the cheapest is Jones oxidation. Jones oxidation. So Jones is just a name for the person who came up with this, and it's potassium dichromate, H2SO4. Some of you may be still using his textbook. All right, so if in Jones oxidation, you are going to take, let's say, a alcohol and make it into a ketone or an aldehyde. So here your starting material is an alcohol. So let's say you have an alcohol like that. You must have a hydrogen, which is why you cannot do tertiary. So let's say I take this and I have an R group here, let's say a methyl group here. So here, this makes a chromate ester. And so it goes through a chromium trioxide. It produces a chromium trioxide in situ that then reacts with this. So the chromium trioxide is kind of a critical moiety here. Without that, it's not going to go. And if you got caught for DUI, this is a nice bright orange color. It's in a tube. And then so the officer will say, hey, walk over, Sonny, and blow into this little tube. And if you blow into it and it turns green, that means you've had a few. And that's what you see here. So here's your chromium trioxide. So here chromium's got lots of oxygens, electron deficient. This nucleophile attacks it, opens this up. And then here it is, your oxygen then is going to be hanging on to that chromium for the rest of the ride. And here's your O minus, and you have 2 more oxygens here. And let's say we have a hydrogen and a methyl here. This is a secondary. All right, so then you have a plus here, and there's water that can deprotonate. This has a pKa of around -2. This has a pKa, this is about -6.5. So you can think of this as deprotonating this. And it's an inacid medium, so, you know, OHs, cations are fine. So here we have this oxygen here, and now you have a chromium OH and double bond, and a double bond here. Here it is, we have this molecule like as an intermediate here, and we can take this and then oxidize this some more. You can think of either this oxygen pulling it off, or you have plenty of water in here, and your water will act as a very, very, very weak base and pull this off. Those electrons will then run into here. That's going to kick off this pi bond. Here goes the chromium, which will kick off a pi bond because the pi bonds are kind of weak. And that will then get protonated. So here you have a oxygen double bond, which is what we want. You don't have any more hydrogen, so your oxidation will stop here. So now you can see that the chromium is, well, you're going to have lots of acid here. So your acids are going to protonate this, and you will get chromium H2CrO3. So we'll leave it like this, and then this is going to protonate with a hydronium, and you will get H2CrO3 with that CrO, O, and these molecules are going to be there for some time until you just distill this off, and so this is going to come off. So H2CrO3, that is not a very oxidizing compound, so you can just take that off. So this is one way of doing an oxidation. We're going to come back and see a couple more ways in which we can do an oxidation. See you next time. Bye.